So yes, so the topic of my first lecture on quantum trajectories is quantum trajectories as unravellings, or how does the nature of the trajectory depend on the detector, and does it really? Okay, so this is, I put Pierre Guillemin as well on the, as the speaker, because he's going to give the middle third of this talk. And we'll see what he'll be talking about. And then I'm also listing Jay Gambetta and Shakib Darianush because in the last third of the talk, I'll be presenting some sort of more recent work, in other words, in the last 15 years, work done in the last 15 years, and they were co-authors on that work. Okay, so yes, so those who came to my talk on Monday know I'm in the Centre for Quantum Dynamics at Griffith University in Brisbane, and this work is also supported by this Australian Research Council Centre of Excellence. Okay, so this is the outline of the talk. So I'm going to begin with a brief history of quantum trajectory theory, which I know you've heard little bits and pieces of already, but I'm going to try to give a sort of unified view of how it all came to be. Then, and part three, except for the very recent history that Pierre will talk about in here. And then the last third, it will be on this topic of unravellings and actually testing this detector-dependent property. Then I'll conclude. Okay, so a brief history of quantum trajectory theory. I'm going to go back all the way to 1913, which is when quantum jumps were introduced into quantum theory by Bauer. And so here's a quote from Bauer: "The passing of the systems between different stationary states cannot be treated using ordinary mechanics and is followed by the emission of a homogeneous radiation for which the frequency is given by this relation here involving Planck's constant." And then, so that was, yeah, more or less what Bohr said. He didn't write down actually dynamical equations. Was a few years later, Einstein in 1917 actually wrote down rate equations for the jumps between levels of an atomic system, and he made this comment about them: "The theory leaves the moment and direction of the elementary processes, in other words, the jumps, to chance." So so for both Bohr and Einstein, these jumps were regarded as objective microscopic physical events. The atom, as Bohr said it, makes a transition and then a photon comes out, although he didn't use the word photon because that would not be invented for another 10 years roughly. So then moving on to, I mean, there's a lot of things they didn't say because quantum theory hadn't really been developed. We're now in the 100 years of the sort of real quantum theory, the new quantum theory having been developed. And at least for Schrödinger, he was exasperated by the fact that even in this, that his beautiful wave equation did not seem to have banished quantum jumps from the theory, but rather people were still talking about them. And as he said, if I'd known we were going to have to go on having all this damn quantum jumping, I would never have got involved in the subject. Okay, so that's the very early history. Then in 1930, the famous paper by Wigner and Weisskopf was the first to actually derive from first principle, using the nascent quantum field theory, the rate for spontaneous emission of an atom. And then after the war, physicists upgraded, so starting with NMR and moving on to other fields, upgraded from just writing down rates to actually writing down what we call a master equation. So that's an equation for a density operator or state matrix like this. And so using the Born Markov approximation, typically we get equations, well, we would like to always end up with equations of a form like this. So here's an example, again, describing spontaneous emission, for example, of a two-level atom. So we have this term, which is sometimes called the Lindblad term, has this structure here. This is the way that I'm defining it. where sigma minus is a lowering operator, gamma is a spontaneous emission rate, and H is a Hamiltonian, which in everything that I'll be talking about is an interaction frame. So we're not worrying about the fast rotation of the atomic, like the difference in energy levels between the ground and the excited state. It would just be Hamiltonians on top of that in the interaction frame with respect to that free Hamiltonian. So for example, in resonance fluorescence, if you're driving the atom on resonance, then that Hamiltonian would just look like proportional to, say, a sigma X operator. Okay. So in all this period, so from 1930 all the way up to about 1985, most physicists were not actually talking about quantum jumps. They just, I mean, there definitely were exceptions, but most physicists just shut up and calculated averages, including averages for photocurrent correlations. And yeah, so this was what I call the long night of quantum jumps. And then let's make a jump from the post-1993 or 1993 on, roughly, period, is where we have a new understanding of what quantum jumps are. And that is that to understand that the master equation, as I wrote down on the previous slide, is derived by ignoring the bath, or mathematically tracing over the bath. But this is not always the appropriate thing to do, because that's, yeah, it's just ignoring all the information that's in the bath. But often we can get information out of the bath. We measure the bath. That's how we get photocurrents. That's how we get the things that we calculate the correlations for. So the measurements on the bath will yield information about the system. And moreover, if the Born-Markov approximation is a good one, this is maybe a little slightly bold statement, but it's good enough. If it's a good one, then the bath can be measured repeatedly on a timescale which is fast compared to the interesting system evolution timescale, without invalidating the master equation. So, in other words, putting a photodetector to detect what's coming out of your atom is not going to impose some sort of quantum Zeno effect on the atom. The atom will obey, on average, the master equation just as it always does. So I call this process monitoring the system. I think that's a useful word because for the idea of a continuous measurement on the bath to give information about the system. And if everything was perfect, so if I started with pure states, and if I did perfect measurements on my bath, then it's elementary to see that then we're going to get entanglement between the system and the bath, and from the measurement on the bath, we would collapse the system into a pure state as well, which we call a conditioned state, and so that's what this little C stands for here. And so to use another word, so which this is not due to me, this is Howard Carmichael, who'll come up later. We say that the stochastic evolution, so it's necessarily stochastic because we're doing measurements in quantum theory. Measurements in quantum theory have random results. And so this process, this continuous in time process, is a stochastic process. And as I said, it doesn't invalidate the master equation, which means that on average, that's what this E stands for, an expectation value, or ensemble average, if you prefer to think about that, of this projector is just going to be rho of t, the solution of the master equation starting from the initial state. Okay, and then the other thing which, yes, was known and useful and interesting in 1993, and Klaus talked about this, is that if I have a high dimensional system, so then my state vector lives in this d-dimensional complex vector space. But of course, rho lives in a d squared dimensional complex vector space. And so if d is very large, then rho might actually just be too big to store on a computer, especially the sort of computers that existed in 1993, or at least that physicists could afford to buy in 1993. But this may not be too big to store. And that means that it's actually useful to consider an unraveling in order to calculate averages. So by using a finite ensemble of stochastic state vector evolutions, for each one of them, one can compute an average of some quantity of interest, and then take a finite ensemble average of those is going to approximate the solution that you would get if you could solve the master equation. Okay, and that's the other usefulness of that. Okay, so that's where things were in 1993, which is very different from where they were in 1985. So what is it that happened in the intervening period? So again, Klaus already talked something about this, but I want to give a slightly longer view history of the things that led up to it. So the roots, I think, go back to photo detection theory in the 1960s. So this was work by Mandel, Glauber, and Kelly and Kleiner. And then in the 1970s, this was applied to atomic system, particular resonance fluorescence, exactly the example that I was talking about, by people like Mollo and Cohen-Tanucci and Renaud. And even then, in the 1970s, so these people, Cohen-Tanucci and Renaud, they were one of the few people who were talking about quantum jumps in this period. They used the terms. Mollo never used the term, but implicit in the way he worked out interesting properties of correlation functions in resonance fluorescence was a concept of a waiting time. And the simplest way to say what that waiting time distribution is, it's the waiting time distribution between jumps. So that was a crucial part of the calculation that he did. Okay, so that was, there were developments which were happening then. But the really important kick, which changed things, was experimental progress. So in particular, the ability to trap a single line, and Klaus gave a beautiful movie to illustrate this. Hopefully everybody saw his talk yesterday. So he also put up a picture that looked much like this. So we have the particular experiment that was that came to fruition in the mid-1980s was this atomic shelving experiment, where you have, to simplify things, a 3-level atom with a strong transition between the ground and this excited state, and a very weak transition between the ground and this excited state. And so most of the time, the atom is getting excited up here and just Rabi cycling around, occasionally making a spontaneous emission down to here, but occasionally in the sense that it's actually coming out in a visible to the human eye rate of light being emitted on this transition. But then, if it's in the ground state, there's a chance that it will actually get excited by this by the laser on this transition here, the weak one. And then once it's in this excited state, this is a very long-lived excited state. And so if it gets up here, it stays stuck here. At least this is the intuitive picture. And it's going to stay up there for a relatively long time until eventually it will make a jump down to the ground state, and then you'll start getting light come out. So this is the dark state, as Klaus talked about, and this is the bright manifold where you actually see the light coming out. Okay, so the picture I gave you, the explanation I gave, was in terms of quantum jumps, because that's by far the easiest way to explain what's going on. But at this time, there were, in the early to mid-1980s, people knew that these experiments were coming up. But there were some people who were quite wedded to the master equation idea, which just says, an open quantum system is described by the master equation. You have smooth evolution. What are you talking about quantum jumps? Of course, there's no such thing as quantum jumps, right? That's what people thought, back in the 1910s and 1920s. Okay, we've moved on from that. But a lot of other people knew better. And so there are actually a whole bunch of people who were doing theory at this time to either predict or explain what was seen in the experiments. Oh yeah, so there's a picture. So this is from one of the papers, the Wineland group, the PRL in 1986, showing the same sort of random telegraph process or blinking of on and off photo count from this atom. Right, yeah, so there are a lot of people who worked on this, so this is not a list of all the people, but the ones who are most important to the story were the groups of Zoller, Marta, and Walls, and Cohen-Tanucci and Dhar. And they took their inspiration from different people who'd done work on this in the 1970s. Not surprisingly, from the French group, there's a line going there, a very strong line going through that school. But for Zoller and Marta's Walls, as well as the work of Mollo, they actually were directly influenced by some work in mathematical physics so Davies is a very famous name in the foundations of the theory for quantum measurements. And in the 1970s, and then with Srinivas in the early 1980s, worked out how to describe continuous measurements in quantum theory. And that was something that this group was aware of, and they actually used that in their description of quantum jumps, basically. So quantum jumps were definitely now being talked about, and were in the air, but people were not writing down explicit stochastic equations. Okay, and so the big change when they did occurred around, so papers submitted or coming out in 1991 or 1992, again were these, so I put bold around them here. There was another experimental kick to why the theory went in that direction, and again Klaus mentioned it yesterday, which was optical molasses, this using magnetic and laser fields to trap atoms in 3 dimensions, was done in the mid-1980s as well. And this is a very difficult thing to simulate. And Klaus was, yes, so Klaus is really the one who should be telling you about this because he was directly involved. But the question of how do you simulate an atom in 3 dimensions with multiple levels, it's a very big Hilbert space, and this was a real problem. And so then this, along with so Dalaba, obviously the author in common here, but with Yves Cassin and Klaus Momme, came up with this idea that the quantum jumps suggested by the theory here could actually be generalized to any atomic system undergoing spontaneous emission and could be used to simulate usefully a phenomenon like optical molasses. And then almost at the same time, Zoller, again, the same name from here, and various other people came up with the same idea with, I think, the same motivation to do that. Okay, so that's the big, I think, changes what happened between 1986 and 1992. Okay, so again, so just to contrast then between going back to what in 1913, where we were. So at that point, the emission of the jumps, as I said, was envisioned as objective microphysical events. And the way you said is that the jump occurs when the photon is emitted, right? Whereas in modern quantum jump theory, we can think of the jump as resulting from perfect monitoring of the bath, producing a pure conditioned state, blah, blah, blah. I think I've said all that as well. In this version, it's part of quantum measurement theory, and the jump occurs when the photon is detected. Or if you want to be even more careful about how you say, and not talk about the photon as a physical object, before it, it's not try to imply that it even existed before it detected. One can say that the jump happens when a photo detection occurs. Okay, something just in your apparatus. Okay, so the other major development that I want to talk about, or the next one, is the idea that it's not just all about quantum jumps. So you could say from this previous slide where I was talking about the detection or emission, like, okay, yeah, okay, there's a difference, conceptual difference, but why should we really care, right? Why should we worry about whether it's a photon which has been emitted or a photon which has been detected, which causes the jump? Well, if that was the only way to detect a field, then we probably shouldn't care. Right? But it isn't, okay? Because for any Markovian system described by this average sort of dynamics here, not only is it unchanged by measuring the bath, but it's also unchanged by any different way of measuring the device, the field, the output, whatever I said before. Okay, we can process the field before it hits the detector by, for example, adding a local oscillator at a beam splitter here. So this is a sort of cartoon version with a parabolic mirror and an atom in the middle. So we can just imagine that the light all comes out in one direction, and we can add a local oscillator to it before, as I said, it enters the detector. So mathematically, this corresponds to this transformation on the operator appearing in the Lindblad term. It gets a field added to it, and to maintain the master equation is the same, we also have to change the Hamiltonian like this. But that's a transformation which does nothing to the master equation overall. But if I think of this as being the jump operator, This is now a very different jump operator if I add a C number to it. And there's a particular limit of this which is interesting when I take the limit of the local oscillator. So local oscillator, for those who don't know, that's just like a laser field, okay, in which we idealize as being in a coherent state. So the limit where the intensity of that field, or the amplitude modulus goes to infinity with a fixed argument, which we call the phase. And this then is called homodine detection. We typically actually do it like this with a 50-50 beam splitter and 2 detectors. But yeah, it's basically the same. So this is a different way, obviously, to measure the output field from the system and leads to very different type of evolution, as I'll get to. So where did this idea come from? So this was worked out by Howard Carmichael, who Klaus also mentioned yesterday, in a book. Well, he gave lectures in the end of 1991. It was finally published as a book in 1993. And again, so he was influenced by a lot of the same people. He was definitely influenced by the work of Zoller, Marta, and Walls. He was directly influenced by this early work on photo detection theory because he was really trying to understand how to put these two approaches together, this quantum jump approach and the photo detection theory. How are they consistent? But then in terms of the homodine detection, that came out of another experimental direction, which was quantum squeezing experiments, which also came, like the definitive experiments were done in the mid-1980s. So a lot was happening then, which got on, which had this influence on the theory. So yeah, so Howard Carmichael was really trying to understand how to deeply understand the way that we measure squeezing, which is with homodine detection. And how is that consistent with the way which we typically measure atoms, which is not, which is just by counting photons. And so then he came up with this idea of, so that's just a trace of squeezing, just to fill the bottom of the slide. Yeah, so he came up with this idea of different unravelings of the master equation. So again, we've got a fixed master equation up here, as before, and this is the quantum jump unraveling. So SSE stands for stochastic Schrodinger equation, if I didn't define it before. And so if we write that out explicitly as a stochastic Schrodinger equation, it can look like this. So here dn is a counting process, so it's in any infinitesimal interval, it's either 0 or 1. And so I can think of the current as being that divided by dt, so it's a series of delta functions. And the mean of dn, oops, I left out a dt, so that's actually what I've written here is the mean of the current. Yeah, is given by this expression, the average of the C-dagger-C operator for the quantum state. So if dn equals 1, then essentially you apply this on the state, which just takes away the state and replaces it by the state with C acting on it, and they're normalized. And if dn is 0, then I can ignore this term, and I have this smooth evolution here, which is not unitary evolution, right? You have this Hamiltonian, but you could think of this as being a non-Hermitian Hamiltonian, if you like, and then this other term which ensures that it stays normalized. Okay, so that's quantum jumps written out explicitly as a stochastic Schrodinger equation, whereas quantum, from homodine measurement, one gets a quantum diffusion unraveling. And so as I said, Carmichael was the first person in optics at least to write this down. And so this is a stochastic equation which instead of involving a dn, involves a dw, which is a Wiener process, and that appears also in the current, normalized in a convenient way. It also depends on the mean of a system operator, but it has this Wiener noise in it. And yeah, I've defined this, the actual what goes in here depends on the phase of the local oscillator. And yeah, I assume everybody knows what a Wiener increment is, hopefully. Okay. Okay, so just to illustrate the differences, so these are some pictures from my textbook with Jared Milburn. So here's some quantum jumps for a two-level atom being driven. I've done this in terms of the blocks, so it's all for pure states, so I've done this in terms of the block sphere angles theta and phi, or actually cos theta and phi. So yeah, everyone knows the usual phi around this way and theta this way. And so yes, with quantum jumps, one gets these discontinuous evolutions. So you could also think of this as the excitation. So 1 is the excited state, minus 1 is the ground state. And you get these smooth periods of evolution, followed by jumps where the atom just pops down to the ground state. And meanwhile, the phase is doing something interesting, because in this case, we put in a little detuning as well, just to make that interesting. In this one, this is homodine detection with no detuning. And this is illustrating a quantum diffusion process. So you see there are no jumps here in the energy, but it's everywhere non-differentiable. It's because it's like a Brownian motion process. So you still have some parts where it looks fairly smooth, but there's actually noise everywhere on these trajectories. You might think it looks like there are jumps happening in the phase, but that's just because whenever you go through the ground, like the North Pole or the South Pole, your phase is undefined, so it can go in with one phase and come out with a different phase. So that's the reason that it looks like there are jumps happening here. But if you look, they're only when it's either at the ground or excited state. Okay. And by the way, yeah, I'm happy to take questions during the talk, in case that wasn't clear. Okay, I think we're getting close to something, aren't we? But not quite. Okay, so far I haven't said, why am I giving this talk? Why am I giving historical perspective? Well, because I'd say I am a small part in this history. So I'm not in the first generation, if you like, of people who worked on these quantum jump theories, but I was not long after. So in 1991, when all the exciting papers or books were being written, I was in my honours year, so that's fourth year undergrad year, doing work with Jared Milburn on a number of things, but one of them was attempting to describe quantum feedback. And then in January 1992, so just before I started my PhD, I was at a summer school at the Australian National University, and Howard Carmichael was one of the lecturers, much like, you know, this sort of summer school here, except that he wanted to give an extra lecture. And so they said, okay, we'll schedule a lunchtime lecture. So people can go along to that if you like. And the extra lecture he gave was based on the lectures he'd just given in Brussels on quantum trajectory theory. So that's completely different from what he talked about as his official topic in the school. And that was probably the hour that had the most influence on my career. Because at least this is the way it seems to me in hindsight. Probably this is a flattering way. This is probably not actually the way it happened, but the way it seems to me, the way I remember it, is that after his lecture, I immediately saw that what he talked about, the quantum trajectories he talked about, was exactly what we needed to do a correct theory of quantum feedback. So my part in this, is so the extra arrow that comes in here is that because of Jared, because he'd been interested in feedback for quite a while, we were interested in this question about how to quantize classical feedback control, and then having learned about Carmichael's work, we immediately set to work to write some papers about doing quantum feedback with that theory. But I'm not going to talk about quantum feedback much at all. What I want to talk about is the implications of this way of thinking about quantum trajectories. And that's because if you want to use this for a topic like thinking about actually modeling an experiment with quantum feedback, you have to take quantum trajectories seriously. And what do I mean by that is that real detection is not perfect. Okay, so this idea I've been talking about all this time with, let's assume everything is perfect and, perfect detectors, blah, blah, blah. You get a pure state, a stochastic Schrodinger equation, isn't it beautiful? That's not the real world. In the real world, like real systems leak, so to speak, in the sense that not all quantum information in the output field is going to make it into the detector. Particularly if one has an atom, it's actually very difficult to get much of the output field into a detector at all. And detectors themselves are inefficient. And so this was something which we addressed in this January 93 paper. A little bit later, we also, in this paper, which has far too much in it, but one of the things that has in it is dealing with the fact that you can have thermal or more general types of noise in the fields themselves. that also has implications. And much later, like 10 years later, I did some work on other imperfections like dark counts and finite bandwidths in the detector. Anyway, I'm not going to talk about these things, but just to illustrate, this is the sort of thing one has to worry about. So the implications of this is that the actual condition state is not going to be a pure state. It will be a mixed state. And its evolution, so this is the term that I use at least, its evolution is not going to be described by a stochastic Schrodinger equation, but rather by a stochastic master equation. And again, we introduced it there. So unlike a stochastic Schrodinger equation, a stochastic master equation is not useful. It's not a useful tool for simulating master equation averages. There are little caveats here, which I'm not going to mention, but that's what if you see a symbol like this, that means there's a caveat. So in that sense, it's completely orthogonal to what most people were talking about quantum trajectories for around this time, 1992, 1993. So it's not useful for that, but what it is useful for is for describing feedback control, as I said. So if one has so typical feedback might look like this. So modeling it as modeling it as a Hamiltonian. So we have some system operator multiplied by some function of functional of the measurement record up to that time. So this is just a very simple filter, for example. That's just an example of typically how feedback might be done in an experiment. So basically one could just write down the stochastic master equation, and I haven't showed you what that looks like, but one could write that down and then just write down an extra term with a commutator with this Hamiltonian, and there's your model for quantum feedback control. And you can simulate that, and would actually simulate how well you would be able to, if you take then ensemble averages, it would tell you on average how well your feedback would be working. So of course there are some particular types of quantum systems where one can use analytical tools, but for generic quantum systems, numerical simulation like this seems to be the way to go. No, sorry, so H is a filter function and J here is meant to be the current, the observed current. Yeah, the observed data. I hope, maybe I didn't actually use that. Well, so J is like this J here. It could be a direct or it could be a homodyne, yeah. Okay, and then as a segue now, but the other mathematically nice thing, I'm going to come back and get back into the swing of this story after the interruption, the invited interruption from Pierre. But yes, so the other thing which one can get from this master equation, stochastic master equation formulation, is actually a way to see that the jump and diffusion unravelings are not as different mathematically as they look like in the slide when I showed you the stochastic Schrodinger equation. So pass on to Pierre.
Hello, can you hear me? Thank you, Howard. So my name is Pierre Guillemin. I'm invited here as a special guest. And the reason is that I visited Howard Wiseman in Australia last year for 4 months, mostly to discuss foundations, but we also discussed a little bit quantum trajectories. And we found a way to unify the diffusive and the jump stochastic master equation. So the goal of this second part of the lecture is to show you the unification and why we think it's interesting. But first, we'll start with the usual formulations of here the jump and the diffusive stochastic master equation. And I'll spend a little bit of time on this slide because I think it's important to understand well what these two mean. All right, so let's start with the jump equation. It describes the evolution of a quantum system monitored by a photodetector. So in this case, I'm only monitoring a single detector, which is the SIG. And the picture you can have in mind is if you look at the Hilbert space of the system, you're going to start from some initial state. And then one of the stochastic trajectory is going to be some continuous evolution when you have no jump. the no-jump evolution, and then at some time, a sudden jump somewhere else in the state space, and then some continuous evolution, and maybe you have another jump. Okay, so this is rho time t for the first trajectory, and maybe we can show another trajectory. So you start with the same no-jump evolution, and now let's say there is a jump at this time, and no jump until the end. This will be another trajectory. And so this equation describes both how the state evolves in state space and the associated signal. So in this case, the signal is a stochastic process. We call it dnt, up to time big T. And we can plot the signal corresponding to the two trajectories, okay? So here you don't have a jump, and you have a jump at this time. No jump, a jump at this time, up to the end. And the value here is 1 and 0. And for the blue signal, well, you have a jump earlier, and then no jump until the end. And then, of course, if you repeat your experiments many times, you have different stochastic trajectories and different realization of the signal here. So this is what's described by the first, the jump stochastic master equation. And the second, the diffusive stochastic master equation, describes other kinds of trajectories. So again, I'm drawing the abstract Hilbert space. We start from some initial state. And in this case, the trajectory is going to be a Brownian motion-like trajectory in phase space, okay? It's going to wiggle around up to the final time. So this is, say, the first trajectory, and the second is another motion, like this. And so associated to these two trajectories, you have a stochastic process. In this case, it's a Wiener process. Unfortunately, it's a bit harder to draw than the jump process. But let's do this a little bit physically. So you can think of this, I'm going to put quotes, as drawing a Gaussian at each time step, okay? And so I'm going to draw this picture where each little increment here is going to be a dt. And so the process for example, the first red trajectory is some Gaussian distributed noise, where what's important is this, as the Gaussian asset variance dt is of the order square root of dt. And then you have a corresponding process for the blue trajectory, which is another uncorrelated Gaussian noise. But in this case, what we measure is not directly this. In this case, what we measure is a dyt, which is square root of some observable trace. So I'm not going to put the hats, because I'm going to write a lot of equations. So the C's here are the C with hats here. dt plus dwt. So this w is what I plotted here, but you actually have this other part. Okay? And if you want to represent this, how this part evolves in time, well, maybe, so it's going to be much smoother, okay? It's going to be the time evolution of one of the observables. So maybe in the blue case, it's, I don't know, something like this. And maybe in the red case, it's going to be something like this. But what's very important with these equations is to look at the order of things. So I told you this dw is of order square root of dt. This here is of order dt, because you have this dt here. So for a dt small, this is, if you want, much bigger than this. So when you mix the two signals, when you mix the stochastic process and this dt part, well, it will mostly look like noise, okay? But you know that this is hidden inside. All right, and then we have rules to use these stochastic processes. So in this case, we can use, again, physicist rules. When we square the process, because it's either 0 or 1, it's going to be the same. And then we can ignore any term in dnt dt, okay? And in this case, the rules we're going to use is that when we square the process, it's going to be dt. This is a physicist notation, which is going to be fine for this lecture. And dwt dt is 0, okay? And we're going to use these rules, so maybe I should, in our derivations. Right, so what is the difference between these equations and the equation Howard showed just before, the stochastic Schrödinger equation, is that when you monitor a system with a stochastic Schrödinger equation, so basically you're monitoring all the jump operators with perfect detection efficiency. And so if you plot the purity of the state, so it's bounded by 1, between 0 and 1, this is your classical uncertainty, let's say, on the state. In the case of the stochastic Schrödinger equation, you're not losing any information, okay? So the purity remains 1, this is stochastic Schrödinger equation. If you look at the Lindblad equation, then your purity will, depending on the scenarios, but maybe it will start to go down and then go back up. So one example you can have in mind is starting from some Fock state and having a photon loss, where you have exact certainty of the state at the beginning, then you're losing some photons, so you don't know exactly the number of photons, so it goes down. But in the far long time, yes? Yes, Howard? Indeed. Probably smoother. Or maybe it goes like this. And it's a long time. So in the case of the Lindblad master equation, you're probably losing purity as you don't know what the state is, but for a very long time, you know you're going to converge to the vacuum state, okay? So that's why it goes back to 1. And so you can see the stochastic master equation as an in-between, where you don't have perfect information on the system, but you still have more information than Lindblad, okay? So now if I plot the purity on average, this is the average purity of your state, of the stochastic state. Okay, I don't know if that helps, but that's one way to see this master equations. Great, so I think what's maybe a bit confusing when you see this at first is that these are two seemingly different equations. They look different, the measurement back action is very different, and indeed both the stochastic process and the trajectories in phase space are different. But so our goal now is to see why these are, at least mathematically, the exact same equation. So where did the intuition came from? Why do we want to unify this equation? So for my work with Pierre Rochon and Antoine Sillois, we compute correlation functions of the signal, this IT, that Howard called JT, which is dNt over dt or dyt over dt. And when you want to compute the expectation value of the signal at different time, you find this formula, which you can read from right to left. You start from some initial state, you apply the average evolution up to the first correlation time t1. This is like the Lindblad evolution. And then you insert a specific superoperator, which depends on your process, on your detector. So if it's a jump detector, it's going to be this operator, and if it's a diffusive detector, it's going to be this operator. In this case, theta is the Dhar contrast, and eta is the efficiency. So this accounts for misclicks. This accounts for, eta accounts for misclicks, and theta for false clicks. And here you have the efficiency for the diffusive SME. And so the fact that the structure of this formula is exactly the same in both cases was a hint that led to the new formulation. Yes, Tristan? Oh, so this is you, as a user of this formula, you fix them. You say, I want to compute between this time, and then you apply this formula. And so I didn't finish the formula. You have the average evolution, you insert a superoperator, and then you continue the average evolution of the up to time t2, insert a superoperator, etc., up to the end. All right, so this is going to be our guiding light, okay? We want to preserve this structure at all costs. So this is where the intuition comes from, and we like the fact that it's unified, a unified formula. So what I'm going to write in the next is like some abstract signal, dr, which is either dn or dy. And so if you instantiate this formula for just one point, one time, you have expectation value of dr over dt, so it's either dn or dy over dt. And it's a trace of just this guy, so m expectation value of TL. So what I'm going to use in the rest is just this, okay? Expectation value of the signal is a trace of this superoperator applied to m dt. Okay. And maybe I'll write this down because it's an important formula for the rest. Okay, and I'm taking a time as implicit. Okay. Great, so we want to conserve this. We want to define the M in such a way that this is true. Enough of the derivation. I'm going to write the two stochastic master equations, the jump and the diffusive, one on top of the other. I'm going to do transformations on the board following my recipe here. And ideally, if everything works well, we end up with the same equation. So let's go. We start with the jump equation. We have a Lindblad evolution and the measurement back action. This is the first part, and the second part is... Oh, and if I do any mistakes in my calculation, I'm very happy that you correct me. Especially because we're not exactly using the same notations with Howard, so I'm adapting a little bit live. So I'll probably do mistakes. So I'm just, this is a copy of the equation we had on the first slide. Okay, so I'm missing a square root of eta here, and dw. All right, I think that's correct. And so now we're going to transform this equation, and they should look the same at the end. And the first hint to start the derivation is to use the formulation of this equation with the Dhar contrate, theta, which is not very common, but actually shows a little bit the structure. So what we're not seeing here is that there is an eta over eta that cancels out. But if we use the formulation with theta, we will have theta rho plus eta here, and here theta plus eta this guy, and here it's going to be minus theta plus eta times dt. Okay. So maybe the first step in recognizing that these are the same equation is to generalize a little bit the imperfection we can take into account. Second step is that we're going to replace dw here by the signal. So the signal dy is a square root of eta trace c plus c dag rho dt plus dw. Okay. And so to replace dw, I'm just going to do dy minus this. And as you see, I'm doing the modifications in blue, so it's maybe easier to follow. Okay, so dy minus square root of eta trace c plus c dag rho and dt. All right, as you can see, the structure are starting to look a little bit similar. Now, the third step is that we're going to use this super operator M. So let me write it here. In the jump case, it's going to be this. And in the diffusive case, it's going to be this one. So this is the super operator that appears in the correlation function, and this is, in some sense, we want to make this super operator more fundamental. So every time I see something that depends on that can be written like this, I replace. So for example, this is directly M applied to rho, the big M. I'm just replacing this by big M applied to rho. You can see that this is a trace of big M applied to rho. So I'm replacing this by the trace. And the trace appears here again. So let's just replace this. And so in this case, I use the jump-specific operator, super operator. And in this case, I'm going to use the diffusive one. So you see the square root with this is going to be M applied to rho, and the square root with this is going to be the trace. So I can rewrite this as M rho minus trace of M rho rho. And here again, you have the trace of M rho. So you're starting to see our goal here. But we're not done yet. So maybe what I'll do is factorize here by the trace in front. and rewrite all of this. So I factored out the trace, it went away from here and appeared here. All right, so this now looks very, very similar, except for one term, which is this guy here. And because of this, the first part of the derivation started last year in January in Paris, got stuck, okay? I had no idea how to make this term appear in one of the other equation. And if you want, this is a very constrained problem. If you try changing the signal, you need to change the M and everything fails. So I got stuck in January because of this. Any questions? Yes. Theta is the Dhar constraint. It's a positive real valued. And basically you can say, so theta is when you have clicks in the N that are false. The state is not actually jumping. And the rate of click is theta, and the amount of click per time step is theta dt. So for a big time t, you will have theta t clicks that are false clicks. Yes? Theta? It's a rate like kappa for you if you want. So it's on average, you are right, the number of clicks you'll have. So you will not always get exactly this. You're correct. On average, you will get this number of clicks for time t. Yes.
And then in the probability distributed function, which has plus theta dt.
Yes. So we'll see this indeed, the dn. Okay. So I didn't write the full equation, you're right. So probability that dn equals 0 is 1 minus probability that it equals 1. And then the probability that dn equals 1 is going to be this theta plus eta trace 0 cdag dt. And indeed, you see that this Dhar constraint is going to make false counts in the dn. Is what you meant?
No, what I meant is that if you integrate this quantity, then it goes beyond 1. It goes beyond over time.
Why?
Because theta is a constant.
So it's going to be theta times the time, no?
Yeah.
Yeah? So you may have...
This is the probability, that's my problem.
No, but this is an infinitesimal. This is only
Yeah.
probability for a infinitesimal quant.
Yeah, okay, then I integrate it over time.
No, but this is the probability for an infinitesimal quant. Actually, what this expression is.
So how can I get
Ah.
one between C1 and tau?
Okay, so it's condition and roti, okay? So you draw the probability at each time step, if you want, using the signal, using the state you have. But if you want to see, if you put eta equals 0, then you'll just see some random clicks regularly with this specific rate. That's another way to see it, maybe. All right, so end of January, I'm stuck with this normalization. I don't know how to solve it. I forget about this unification. And so we moved to part 2 of the derivation in May. So actually I arrived in Australia in March, so it took a little bit of time before we discussed it with Howard, because I had forgotten about it. But someday I showed this to Howard, and I asked him for his help in unifying the equations. So we discussed it, and later this day, actually during the night, Howard sends an email saying, hey, hi Pierre, took me ages to find, but I have a 202 paper using the form, the ICME form you found also. There really doesn't seem any reason we used it there. I must just have thought it was elegant and felt like using it, but never did so again, as far as I can remember. So the paper in 2002, where this form here is used, okay? And I think maybe what was missing at the time is the guiding light I told you about, this correlation function formula that we want to preserve. It was both, yeah. Yeah. Indeed. And so then I guess most of you haven't worked with Howard, but sometimes he turns to the window, doesn't speak for 3 minutes, looks at the Griffith forest, and comes back with a dark trick. So a way to unify this equation. So it's going to look very mathematical at first, but you'll see that it has important physical meaning, okay? We're going to add a term that is something like 1/1, if you want. So first, I'm going to rewrite a little bit this one by saying the trace of m rho is E of dr over dt. So I'm going to write this dt over expectation value of dn. It's better to see? Yes. Okay, so I've just used this formula to replace the trace. And now what we're going to insert here. So let me put, or actually I'll directly insert it. What we're going to put here is dt over expectation value of dy squared. Okay, so first, why does this work? Dy squared is going to cancel the term in dt. The term in dt, dw are cancelled again, and dw squared is going to cancel the dt. So this is really like 1, indeed. And why is it the same as this one? Is because now you can put a square on the dn. dn is either 0 or 1, so with the square, it's going to be the same. All right, now what we can do is rename our processes with r, the generic variable r. And you see that we end up with the exact same equations, okay? So it turns out that last Sunday at 11, I was working with Raphael, showing him all of this, Raphael Chetrite, right here. And we had another little trick to add to this derivation, which is to replace the expectation value of dr squared by the variance of the signal, which in this case is going to be the same, but it eases a little bit the interpretation. All right, so this is a unified formula. Okay, you have the Liouvillean, this measurement back action, which is now the same, and you just need to specify this M operator here. Okay. So why is it interesting? First, the two seemingly different SMEs have the exact same structure mathematically. Then this first term here guarantees that the evolution when you average is going to be the Lindblad evolution, because the mean is going to cancel with the other mean. The second term here, when you apply it to rho and use the formula for E of dr, is a traceless update, and this guarantees that the state rho remains as trace 1. So if you want it's the same for Lindblad, the update is traceless, and it's the same here. So the structure guarantees some invariance that we absolutely want for our evolution. And then this, I told you, this weird term in the bottom, the denominator, has important physical meaning. And the meaning it has is that usually when we write these equations, we normalize the signal, okay? So we don't need this term. But generically, if you multiply your signal by some value, say 3 or 4, or if you measure in different units your signal, it should not change the measurement back action, okay? The state doesn't care about your signal unit. And so if you replace your signal by some scaling, then because we have our guiding light, we also want to replace our m to scale our m, okay? Because we always want the expectation value of dr to be this one. So what happens if you scale your signal is that you have an alpha that pops here from the dr, an alpha that pops from the dm, and then the variance square is going to give you alpha square, and so all of this cancels out. So this seemingly weird denominator actually accounts for the gauge freedom in choosing the signal units. So now you can write the measurement back action for any signal. It's going to work. And finally, why is it interesting is because maybe this gives an easier intuition for the measurement back action. So one way to see this is to split it and write the left term like this. So I'm splitting the variance and just looking at the left term. You know, when you have a random variable, you can subtract the mean and divide by the sigma. This is going to, okay, if you had a wide Gaussian centered on, mu with variance sigma, it's going to center it on 0 with variance 1. Okay, so this left part of the term is just saying, well, I don't care how spread my signal is. What I care is whether I'm in the middle here or very far from what I was expecting. Okay, so the more you're surprised by your new measurement result, the stronger this measurement back action is going to be, both in the diffusive and in the jump case. Okay, so now this is To generalize a little bit, the usual jump diffusive SME, so we're just summing for multiple jump process and multiple diffusive process, multiple jump process. And with a unification, you can rewrite this rather large equation as just a sum of this measurement back action, okay? And then in each case, depending on your detector, you have a specific superoperator, and this is a probability for the jump process, probability for the diffusive process, okay? So maybe I'll show again. This huge equation becomes this small equation. This is also interesting because if we come back to what I told you was our guiding light, if we generalize to multiple detectors, we can take correlation functions for multiple different signals, right? Where this might be either jump or diffusive and coming from different detectors. And in this case, the formula is the exact same for the correlation functions, except each time you need to insert the superoperator that corresponds to the detector your signal is coming from, okay? So with this, you can compute correlation functions between like jump and diffusive type signal. And so here the MK is either this one or this one. Right, now what's next for this formula? First, I think it has some pedagogical purpose because it's very unified and it explains a little bit the measurement back action. I think it was hard for me to learn about quantum trajectories. So because you have 4 different axes, okay? You have a jump versus diffusive, stochastic Schrödinger equation versus stochastic master equation, linear versus nonlinear, and discrete time versus continuous time. And you have so that's 16 equations you need to learn and understand. So one hope is to try and unify more of these equations with this formula. Then usually what we like in math when we unify formulas is to have unified proofs. So for example, maybe we can have the same exact proof for the correlation functions, but that's still not fun. It's a work in progress. And then you can reverse the plate if you want. So we showed why the usual equations can be written as this formula. And now maybe we can turn the question around and say, does this formula actually characterize all possible unravelings of the Lindblad master equation? So this would be like a physically motivated general structure for stochastic maps, CPTP maps that average to Lindblad. So why do we think this is probably the case? Is that the only allowed stochastic process, if you want your state to remain Markovian, are Poisson and Wiener processes. And then the question is, what should I add as constraint to restrict the form of this measurement back action here, and specifically this M operator? And so maybe the constraint you can add is that this should be a CP map, the update. You also have in the special case of perfect detection that you want an initial power state to remain pure, and this gives you an equation on the M that depends on the L in the Liouvillean. So this is work in progress, but we hope this can maybe be a complete characterization of these maps. And why would we care about this very generic formulation? Well, one example is that people then use this to build new models of the world, okay? So you have, for example, Laios, just in the room. These equations are used to couple quantum and classical systems for semi-classical gravity. So maybe if we have a well physically motivated general form, we can explain the world in different ways. Last slide, and then I give back the mic to Howard. So I'm sorry, this is a lecture, but this slide is a bit for the professionals. So people who know about the ostensible distribution, you can write the most general linear SME given any ostensible distribution, just using this by computing the expectation value with your ostensible state. Okay, I'm not going into detail this, and if you're curious, we can discuss it later. So Howard, I think it's your turn. Bye. Thank you.
I guess I won't finish everything I was planning to, but that's fine. I can squeeze things into the next lecture. Okay, so yes, so that I think that was I think having the pedagogical working through things on the blackboard is probably more important than some of the things I'm going to say. But at least in this lecture, I want to finish the sort of historical story that I began. So on the topic of stochastic master equations, which, as I said, in the quantum optics literature were introduced, or at least, I think generally people noticed when it was introduced by me in 1993. But there's more to it than that. We did not really appreciate the full usefulness and meaning of the conditioned state here. Because more than just being useful for modeling general feedback control, which was the last slide which I put up before Pierre talked, this quantity, if you could calculate it in real time in an experiment, right? If you can process your, solve this equation by processing the current, then this quantity which you've calculated is exactly what you need to determine the optimal control, which you're going to use a bold U to represent that because it could have many variables, the optimal control to apply to your system at that time t, no matter what your objective is for your system. Okay, with the caveat that provided the control objective can be written as what you're trying to do is maximize a function of a form like this. So it's some integral of a local in time operator, which you're taking the expectation value of, and now you're also, so a quantum expectation value of this operator, and then you want the ensemble average of that over all realizations of your stochastic measurement process. But this operator can also depend on the controls that you are applying at that time. So it's a very general type of formula. Okay, so that was not realized by me, okay? This was actually proven in a very formal and discrete time way by Balabkin, who's another mathematical physicist way back in the 1970s and 1980s, who's unfortunately dead now, but he was also interested in this question about how to quantize feedback control. And so, yeah, I think I've just, so the process there's also a question which is very closely related in classical theory of classical filtering and classical feedback control. They really go hand in hand because there's a classical analog of this statement here. And Balabkin put these together in the 1980s in a very formal way. But it wasn't actually until around the turn of this century that Andrew Doty and Kurt Jacobs and collaborators. So initially they independently made this connection of the usefulness of rho for linear systems where things are easy to solve. But then I think Balabkin contacted them and pointed out exactly where what he'd done earlier was a precedent. And so gradually the community came to understand what he'd done. And so in fact, I think we can put in the same time, almost the same time, or actually slightly early for Balabkin. So Balabkin and his collaborator, Barchielli, actually were writing down at this time the same sort of stochastic equations, both for jumps and for diffusion, that people in the quantum optics community were doing. And Barchielli, so the other bit which I've sort of missed out is what's feeding into this was some other work by mathematicians and physicists. So on the mathematical side, with quantum stochastic differential equations, which is different from stochastic Schrodinger equations. And did Pierre Rouchon talk about QSDEs for anyone who was here? No. Okay. Okay. I assume somebody who's probably going to say something about this at some point. But anyway, this was a very critical feeding into also developments in the theory by Zola, again with colleagues Gardner and Parkins, and again to Balabkin. So there's some famous work by Gardner and Collett in the mid-1980s, building on this work. Well, not building on, independent of this work by Hudson and Parthasarathi. On quantum stochastic differential equations. Anyway, all of this mathematics was fed into both work that physicists were doing and mathematical physicists, and remarkably all writing down the same sort of equations at almost the same time. So that was sort of remarkable. Whoops. Okay. What happened then? Right. Okay. Next topic, but we'll see. It really just continues on with yet another thread in the whole scheme of yet another group of people who are writing down the same sort of equations at the same time, but for different reasons. And that's this root of objective collapse theory. So Lajos Diossi mentioned this yesterday. So people, this was really people in the quantum foundations community were wondering about either unifying quantum theory and gravity or just how to solve the quantum measurement problem by inducing objective collapse. And there are a lot of names here. And I put dashed lines here because I'm not an expert on who was influenced by whom. But this is this red thread going down here. So Pearl, Jasan, Diossi, GRW, the famous name. Most people know about it, but there was a long history before then. That's Garadi, Rimini, and Weber. And then I can't remember exactly when, around this time, late 80s, Diossi, hope I'm not misrepresenting it, but they had the idea of like having realized that these equations, basically, when you look on average, they just look like master equations. If you look at the average over these stochastic objective collapse theories, continuous collapse theories, they just look like master equations. So the question you could ask is, well, why not just take any master equation, which people play around with in quantum optics, and just do the same thing with it? Do a stochastic version of that master equation. And so Lajos wrote down a Fokker-Planck version of this, so not an explicitly written down as a stochastic equation. But then a few years later, in '93, Nicolas Gisin and Ian Percival wrote down an explicit stochastic Schrodinger equation with diffusive noise. Again, I don't know whether they knew of the work or discovered it independently, but anyway, they wrote this equation down. And so this is what it looks like. So it looks very much like the sort of equation which I wrote, the stochastic Schrodinger equation, which Howard Carmichael wrote down for homodine detection, but it's not quite the same. And specifically, the noise that appears here is not real noise, but is actually complex noise. So the Ito rules for it are that actually dB squared is 0, but mod dB squared is dt. And this has a very nice property that it's invariant under the transformations that leave the master equation invariant. So you might remember I talked about before that we can, add fields to add like a complex number to the field before it's detected. And if we do this transformation, then the master equation stays the same. Well, that transformation doesn't change this stochastic differential equation at all, this stochastic Schrodinger equation at all. So that looks like it's a pretty special thing to have this property. And they were pretty excited about it and thought, well, surely this must be significant. This must be like the unraveling, surely, like it has such nice properties. And then, so then my little appearance here is because with Jared, we showed that actually this is the same sort of stochastic Schrodinger equation as we had already been, Carmichael had been considering. This is just the one for heterodyne detection rather than homodyne detection. So heterodyne detection is when your local oscillator is detuned from your system rather than being on resonance with it. So it sort of cycles through all the phases, which is why you get a phase invariant equation like this. There's no choice about it. So that was a little bit of a dampener on their ideas, but I'll talk more about the reaction now. Okay, so the overall theme that I'm trying to get across here is the answer to the question of are quantum trajectories detector dependent is yes. Okay. But I want to emphasize that this was, and I sort of made the story as that, well, this was, this is obvious to everyone in 1993, but it was a sort of difficult process to get there. So even in quantum optics in 1989, for example, we find the statement like this. What role does photoelectric detection actually play in the return of the atom to its ground state after each photoemission? We argue that photoelectric detection does not cause atomic state reduction. Projection of the atom into its ground state is caused by the dissipative nature of the atomic dynamics with complete indifference to the presence or absence of an observer. Photoelectric detection merely monitors emitted realized photons. So in other words, like Bauer was right, basically. And now you might be saying, well, this must have been some, completely ignorant person who could possibly be making a statement like that in 1989. Surprisingly, Howard Carmichael. Obviously, he had a change of heart over the next few years as he thought more about the theory. But I think, yeah, just gets across that the field was really not in a very settled state. It was a very exciting time. I missed probably the most exciting part of it. But yeah, the late 80s and early 90s was a time of tremendous change in how the community understood things. And then, yeah, in 1992, Gissin and Percival said, so quantum state diffusion, that's the name they gave to their equation, QSD, is a model for the motion of an individual quantum system in interaction with its environment. The quantum jump model provides a different insight, so they were aware of the quantum jump model, and maybe I should have said, yes, so I don't know, again, I'm not sure if they were actually influenced by this. They were definitely aware of the work of Dalibard, Castan, and Molmer when they published. I'm not sure whether they were influenced by it or not, but yeah, they were aware of the quantum jump model. They say it provides a different insight into the behavior of individual systems, and it remains to be seen which, if any, is preferable. So they still had the idea that, well, one is right, one or the other is probably right, and we don't know yet which. Obviously, they like theirs. But they didn't have this idea that, no, it just depends, you know, the equation you write down just depends on how you're getting the information about the system from the environment. There's no question of which is preferable. It's just, you know, they describe different types of measurement, and in general, they don't, none of them actually describe real measurements because real measurements require a stochastic mass regression. Okay, so again, this question, how are we going? Yeah, okay, maybe I'll start this. I'm obviously not going to get anywhere near finishing this story, but at least I'll start it and I'll maybe finish it in the next lecture. So are quantum trajectories detector dependent? Again, yes, but I think that's not all that can be said. We can say yes in theory, but you can say, but has the theory actually ever rigorously been tested? Can we really be sure that a two-level atom, for example, doesn't really emit a photon and jump to the ground state, as Carmichael thought as late as 1989? Can we be sure that it doesn't actually undergo quantum state diffusion, as Gissin and Percival thought it might in 1992? Or maybe it might be undergoing some other stochastic evolution according to some other objective pure state dynamical model, to introduce a rather ugly phrase, but that's what I'm going to talk about as a general class of models. Can we be sure? Have we actually disproven this idea? Like, we certainly know that it's useful to think about different, like the models, or these models we're using, they seem to agree with experiment, but have we really proven that there can't be some objective dynamics underlying them all? So this is a question, can we derive realistic, I mean, and this is a question that was, 15 years ago was the one I was thinking about, can we derive realistic experimental tests that would rule out all objective pure state dynamical models, including objective quantum jumps and quantum state diffusion? And so by realistic, I mean, for example, not assuming very high efficiency detection and not making some special preparation of the atom in the field. We just want to run the experiment in normal circumstances and see whether we can actually disprove it. So maybe I'll just do a snippet that I think the answer is yes. And yes, we can design experiments to do this. They haven't been done yet. And the route to doing it is to go back again in history to EPR, well, Einstein, Podolsky, and Rosen, and to Schrödinger in their work in 1935. So, just to briefly, for those who don't know about the EPR paradox, so this is one of the ways that it's explained in the EPR paper. They introduce so they have their position momentum argument, but actually they have a much more general discussion where they introduce a general pure state like this with basically exactly this notation just modified. And so this is just two different ways of writing the same state using different bases for Alice, the first party here. And yeah, so this is telling you if Alice measures in the U basis, then she's going to collapse Bob's state in system into one of these states, whereas she measures in the V basis, she'll collapse Bob's state into one of these these pure states here. And they say, yeah, as a consequence of two different measurements performed upon the first system, the distant second system may be left in stage with two different types of wave functions. So for EPR, this was an indication that quantum mechanics was incomplete. Okay, but I don't want to go through that story. But yeah, let's just, the way I want to look at it is that they discovered this phenomenon. Okay, that distant measurements, a distant measurement choice can affect the type of state that your other system collapses into. And hopefully you're already seeing the connection. So Schrödinger in the same year published a paper where he called this phenomenon steering, but there's Einstein doing the steering. And okay, so for both of them, they only considered pure states and projective measurements. So that's how this phenomenon was written. And so some of you might know that actually my work in 2007 with Jones and Doherty, which was formalizing and generalizing this phenomenon for arbitrary measurements and arbitrary states, is actually way more cited than any of my quantum trajectory papers or quantum feedback papers. But anyway, so this is actually where I'm probably these days most known in the physics community. But this is going to be useful if we're going to think about real measurements. So I might stop there and just and maybe continue from this point and explain in the next lecture how we can use this idea, this formalization of EPR steering, to actually design experiments to try to rule out objective pure state dynamical models and leave a little bit of time for questions. Oh, is that's time till questions, is it? Ah, right, okay. I want, well, are people feeling questionful? Is this, should I mean, nobody's jumping up, so maybe I'll just keep going for a few more minutes. Okay, all right. So the way we formalized this in 2007 was to say that demonstrating EPR steering is demonstrating that what we call the local hidden state assumption for Bob cannot hold. Okay, so the local hidden state assumption is just that Bob really has some state. So this is, I'm writing it as a projector pi. So it's hidden in the sense that it might not be known to him, or it wouldn't be known to him, but it might be known to Alice. And it's right. So there are possible, obviously different hidden states that it could, if it was only ever one, then he would know what it is. But there are different possibilities, and they occur with, in a given experiment, they occur with some probability. So this is a model, right? This is a local hidden state model. And we're not going to make any assumptions about Alice, except that, she's a distant party, so she's not directly affecting Bob's state. So if Alice, in this model, right, if Alice makes different measurements, that can only mean different ways of processing the information she has about Bob's state. Right? So in this model, there is no entanglement. It's just there is some real pre-existing state there for Bob, and Alice, Alice might know it, and if she's going to pretend that she has different measurements that she can do, the only thing she could do would be use the information she has about Bob's state to produce results in a different way. And so, so we want to disprove this model, and if we can, we've demonstrated that it's not the case that Bob has a pre-existing pure state, but that what Alice's measurement choice really does, in the EPR steering sense, affect the possible states that Bob has. So in analogy with Bell inequalities, we showed that we construct EPR steering inequalities. So these are, for two parties, they're bipartite correlation functions. Again, and if you violate one, then you demonstrate the failure of the local hidden state assumption, you demonstrate EPR steering. Okay, and I think that would be a good place to stop anyway, and I'll continue for the next time. Thanks. So I think I'll open to questions from me or Pierre.
Questions? Yeah, Klaus. Is there a microphone somewhere? Yeah.
Thank you, Howard, for a really, really wonderful overview of this field. Maybe as an anecdotal remark, Howard Carmichael has a funny comment in his book where he says you cannot simulate with trajectories the absorption of photons from a hot bath. And he has become a newborn believer that everything has to be measured. So he writes, because you cannot see the absorption of emission into a hot bath. So that's almost the anti-comment to the remark he made in 1989. Yes. Of course, he meant the opposite. So that's a funny thing.
Yeah. So he definitely had a Jesus moment.
Yes, absolutely. I was going to see newborn Christian. So that's the same thing.
Any questions, Kate?
So I know we discussed this EPR steering maybe back in 2012 when you visited Berkeley, perhaps. And when I looked into it, I remember there being like an efficiency threshold of maybe 60% that you had to exceed in order to quantify this EPR steering.
Yeah, well, that's the story which I'll get to. Yeah.
And so no one has tested this since then. Is that true?
As far as I know, nobody's
tested it. And because yesterday, I think Benjamin was saying that now there are some experiments out there that have efficiencies in that range. So
okay, so it's a bit hard. Yeah, well, why don't we talk about it after the? It's a little the threshold. It depends on which one we're doing. The simple experiment, the threshold was higher than it was 73%.
73%. Okay.
But yeah. So maybe it's still difficult. I don't know. But yeah, we should definitely. Yeah, this is one of the things I would like to talk about.
So just anecdotally, I tried very hard to improve the efficiency beyond something to get into that regime and felt it to be very, very challenging. And it wasn't sure if I was pushing up something against something fundamental or just hard experiments.
Wow. Well,
but there are experiments that do claim efficiencies that are in the 90%. So it should be possible.
Okay. Yeah.
Just a quick question about this unified picture. So how does the kind of, the discontinuous nature of the diffusion process, as opposed to kind of the smooth nature of kind of the trajectory evolution before you get jumps, do these things exhibit, do they show up in the SME, the unified SME in any way?
Yeah, do you want to answer the question? I can. All right, I have the microphone. Yeah, I think so. So the unified SME doesn't mean that they're now the same equation. They're just, the equation has the same form. So we still have jump and, smooth evolution interspersed by jumps in one case, and a continuous but non-differentiable evolution in the other case. Does that answer the question?
Yes. Can you just point out where in the equation this you would make the change?
So so both what the so it's the same. I guess it's this right. So it's the same equation now. But what this super-operator is would be a different thing. But more importantly for the nature of the trajectory is that the stochastic nature of this dr will be different in the two cases. So it is still the case that this dr is either dn. Well, sorry, so I was going to say dn or dw, but that's not true. It's the record, but the record still either consists of spikes or of this incredibly noisy record. Yeah.
Yep.
So these Bell inequalities are for discrete variable systems. The EPR steering inequalities, these are discrete or also continuous?
So Bell inequalities are not necessarily typically for discrete variable systems, absolutely. But they don't have to be. All that is necessary are, is that even? So it's definitely not. That's definitely not the difference. Okay, that's not the key difference. So these EPR steering inequalities, could be. So you see, like so they did go to infinity. All right. It's not about the nature of the system or necessarily even about the nature of the measurement. There are different assumptions underlying it. So the EPR steering is strictly weaker than Bell non-locality. So if you do a Bell experiment, you are necessarily already doing an EPR steering experiment, but not vice versa. And it definitely is the case that there are people have done generally it's easier to derive EPR steering inequalities than it is to derive Bell inequalities. And so probably for that reason, you find EPR steering inequalities for continuous variable systems, whereas you don't tend to find them for Bell. I mean, there are fewer for Bell inequality because it's just harder to derive.
Just one quick, so, or maybe it comes to your next lecture. The one typical way of verifying this local LHS assumption in the continuous variable is to do this conditional uncertainty measurement.
Yeah, so that is
that one of the EPR steering inequality or no?
That is an example of an EPR steering inequality. Yes, yes. So I didn't give the whole story there because yes, Margaret Reed and Peter Drummond, they had already come up with ways to make more practical tests of EPR steering, but they hadn't really conceptualized it in this way. They sort of just did a more direct, or what would be analogous to what EPR did, but with noise in it.
So these are still are they still connected with the entanglement quantification, or is this just the?
So again, so entanglement. So all of the so EPR steering is a proof of entanglement.
Okay.
And Bell inequality is a proof of entanglement. But again, it's a hierarchy. So an entanglement, if you violate an EPR steering inequality, you prove that the system is entangled, but the contrary is not true. So again, you could violate an entanglement witness, but that doesn't mean that you've demonstrated EPR steering.
We can take 2 more questions. Maybe let's start.
So, given that you have these 2 different descriptions, could there be many more that we could formalize? And if so, is it worthwhile formalizing them?
Yeah, well, that's definitely a question for Pierre. But if you really want to, yeah, okay, all right, I will. Okay, good.
So good argument that we don't really have more than this, that if you want the state to remain a Markovian, you need the stochastic process to be either Poisson or Wiener. This is a result from a classical stochastic theory. So the driving process is either Poisson or Wiener, you don't have another choice. And then you maybe have a different choice for the signal you actually measure and the corresponding M. So for example, if we never had Dhar in our detectors, we would never have put this theta in here and the theta rho in the M. So maybe you have other imperfections or other schemes of detections where you will change the probability of the signal being measured in the form of this big superoperator M. I don't know if that answers your question.
Yeah, so I think that's right. We're not going to find things other than jump or diffusion, but the question about what the effect of the jump and the diffusion on the system is, maybe we probably have not completely characterized what that is, but by the equations written down before. There are going to be more general processes in that sense.
On the same issue, of course, the unravellings are like different Krauss maps representing the dynamics of the system. So it could be a further line in your beautiful overview of the many different theories that can be connected. So we have, of course, Krauss map means that every evolution has to be written as a sum of POVMs acting on the state. And I think that the equivalence you show is a little bit saying that you have a POVM formulation of the quantum jump trajectories, you have a POVM formulation of the stochastic diffusion equation or the stochastic master equation. And that's actually what you proved explicitly with your R operator representation here. Now we can go to the same POVMs that can also be written out of that equation.
Yeah, I think that's a useful way to think.
And connection to quantum
maps is a useful way to think it.
And then a connection to quantum measurement theory, which could be the line with Krauss and Peres and all these quantum measurement.
Yeah, so Davies and Krauss were the two sort of, I didn't put Krauss's name up, but they were at the same time using different language, developing very similar ideas. Yeah, but I don't think Krauss ever developed a continuous measurement. No.
That's an excellent point to close on. We'll leave the further questions for the break. Yeah, I'm sure there's some more, but we can do that in the break. Let's thank Howard and Pierre again.